So let's get right into it. We're going to talk about a pretty wild idea in the fight against climate change. What if we could take carbon dioxide, our biggest greenhouse gas problem, and lock it away for good by turning it back into solid rock? And even cooler, how a new digital technology is giving us this incredible, almost X-ray vision into how it all works.
Everything really starts with this number, 420 parts per million. That's the concentration of CO2 in our atmosphere. And to put that in perspective, it's a level we haven't seen in, well, a very, very long time. It's the number that's driving so much of the climate change we're seeing today.
Which, of course, leads to a huge question. I mean, even as we're racing to adopt renewable energy, we've still got to deal with all the carbon that's already up there, plus the emissions we can't just shut off overnight. So where in the world are we supposed to put all of it? We need a seriously big solution. And that brings us to our first big idea. For a lot of scientists, the answer is literally right under our feet. We're talking about figuring out ways to hide all that carbon deep in the earth and keep it there safely for a long, long time.
Now, the official name for this is geological carbon sequestration, or GCS for short. The whole concept is pretty straightforward. You grab CO2 from big sources, like a power plant, you compress it down into a dense, liquid-like state, and then you pump it deep underground into rock formations where it can stay put for millennia. And once it's down there are a few ways it gets trapped. You can hold it under a solid layer of rock it can't pass through, or let it get stuck in tiny pores. But really, the gold standard, the one everyone's excited about, is that last one, mineral trapping. This is the most permanent, most secure way to do it. Why? Because the CO2 literally stops being a gas. It has a chemical reaction with the rock and becomes a solid mineral. It can't leak out because it's not a gas anymore, it's part of the rock.
Okay, so that whole idea of mineral trapping, of turning gas into a solid, leads us to a specific type of rock. See, to make this reaction happen, you need the right kind of rock. And it just so happens that one of the most common volcanic rocks on the planet is basically perfect for the job: basalt. And this is what makes basalt so special. As researcher Sourav Motiani points out, it has this built-in advantage. It's absolutely packed with elements like calcium, magnesium, and iron. So when water that's full of dissolved CO2 washes over these elements, it kicks off a chemical reaction that turns that CO2 into solid carbonate minerals. It's just natural chemistry. So, to put it another way, we're not just storing a gas underground and hoping it stays there. We're actually starting a natural process that literally transforms pollution into stone. This is what makes basalt so incredibly promising. It's like nature built the perfect lockbox for CO2. And the scale we're talking about here is just mind-boggling. Let's take the Deccan Traps in India, for example. It's this enormous area of ancient lava flows. It covers over 500,000 square kilometers. One study estimated that this region alone could have enough space to store gigatons and gigatons of CO2. The potential is just massive. And this isn't just some theory cooked up in a lab. Real-world projects have already proven this works. You've got the CarbFix project in Iceland, which found that over 95% of the CO2 they injected turned to solid rock in less than 2 years. That's way faster than anyone thought possible. Then there's the Waliwilla project in the US, which successfully pumped 1,000 metric tons deep into basalt. So yeah, the science here is solid, pun intended. So here's the challenge, right? How do you actually study these reactions? They happen miles underground, under insane amounts of pressure, and they take time. We need a way to see what's happening inside the rock as it changes. And that brings us to the really clever innovation in this research, creating what's called a digital rock. The old way of studying rocks was, well, pretty destructive. You'd have to crush them, slice them up, and one test that basically destroyed your sample. It was slow, and it only gave you a rough average of the rock's properties. But this new way, digital rock physics, it changes the game. It's totally non-destructive. It's fast, and it lets you zoom in and see every tiny little detail, right down to the individual pores. So what is digital rock physics, or DRP? Honestly, the best way to think about it is like giving a rock a CAT scan. A super high-resolution scanner takes thousands of images to create a perfect 3D digital model of the rock sample. It captures every single crack, every pore, every pathway. You end up with a digital twin of the rock that you can then take into a virtual lab. The process itself is really elegant. First, you do the imaging. You scan the physical rock. Then,
You process all those scans to build this beautiful, detailed 3D digital model. And finally, the fun part, simulation. You can run all kinds of virtual experiments. You can flow digital water through it. You can squeeze it. You can test its strength, all without ever having to touch the original rock again. So this brings us to the core of the research we're looking at today. The scientists used this amazing DRP technology to run an experiment. They wanted to watch that mineral carbonation process happen inside a real piece of Deccan basalt, almost in real time. For 65 days straight, they took a sample of basalt, they put it under the exact kind of temperature and pressure you'd find deep underground, and they exposed it to CO2. The whole point was to simulate what might take years and years in a real reservoir, but to crunch it down into just over 2 months in the lab. And the experiment itself was just beautifully simple. It was a before and after picture. They took a super detailed before scan of the rock, then they put it through that 65-day CO2 treatment, and when it was all over, they took another incredibly detailed after scan. By comparing those two digital models, they could see exactly what had changed inside the rock, down to the micron. All right, so what did they find? This is where it gets really cool and where you can see the true power of digital rock physics. The scans gave them hard, measurable proof that the CO2 was fundamentally changing the rock.
First off, they looked at something called permeability. That's just a fancy word for how easily fluid can flow through the rock's internal network of cracks and pores. And what they found was that after the CO2 treatment, the rock's permeability went down. This is a huge clue. It suggests that new solid minerals were actually forming and starting to clog up the old pathways, which is exactly what you want to see if you're trying to trap carbon.
Next, they tested the rock's elasticity, basically how stiff it is. And here, they found the exact opposite trend. The rock actually got stiffer after reacting with the CO2. And that makes perfect sense, right? If you're filling up empty little holes inside the rock with brand new solid minerals, the whole structure is going to become more rigid. But for me, this is the real showstopper. These images are simulations showing how fluid would move inside that digital rock. Before the experiment, you see the original flow patterns. But after, look at that. The pathways are totally different. Some are blocked off, new ones have opened up. It's the smoking gun. It's visual proof that minerals were dissolving and new ones were forming, completely rerouting the rock's internal plumbing. So what's the big takeaway here? Well, the experiment was a huge success on 2 levels. First, it confirmed that yes, this Deccan basalt reacts with CO2 just like the theories predicted, locking it away and permanently changing its own structure. But almost more importantly, it proved that digital rock physics is an absolutely incredible tool for watching and measuring these changes in a way we never could before.
And that leaves us with this one final, pretty profound question. We know we have the right kind of rock. We know there are immense quantities of it all over the world. And now we have the digital tools to study and monitor the process with unbelievable precision. So could this idea of turning our pollution back into stone become a real cornerstone technology in how we tackle climate change? It's a pretty amazing possibility.